Okay, all right. Thank you so much for the invitation to this seminar series. Hello, everyone. My name is Chen Chen. I'm an assistant professor at the Center for Research in Computer Vision at UCF. And today, my talk is towards efficient, adaptive, and robust deep learning. Okay, so before the talk, I want to give a little bit background about myself. So I got my bachelor's degree in 2009 from China. And then I got my master's degree in Mississippi State in 2012 and my PhD degree in electrical engineering from UT Dallas in 2016. And after my PhD graduation, I actually come to UCF, did my postdoc from 2016 to 2018. And after that, I take my assistant professor job in UNC Charlotte in the ECE department from 2018 to 2021. So since last year, I've been with UCF as assistant professor. So my research area are focused on two regions. One is the computer vision. So in this area, I'm focused on several subtopics. For example, object detection and tracking, action detection and recognition from videos, and human 3D or 2D pose estimation, and image semantic segmentation, and image restoration. And on the machine learning side, I'm interested in efficient deep learning and federated learning. Okay, so here's just a couple of research highlights. So my research is sponsored by NSF and also industry partners like Intel, Adobe, and the Peak Technology. And I was also fortunate to receive the CES Infrastructure Fund last year. Thanks UCF and CES for the support on my research. And my PhD student just received the Best Paper Finalist Award from CVPR 2022. That's the top venue in the computer vision and the machine learning community. And I have a H index of 53 on my research. And at UCF, I teach the graduate level course, medical image computing. Okay, so I'm sure you've all heard some of the buzzword, right? Like artificial intelligence, AI, and the deep learning. And deep learning has been very successful in the recent years in many domains, right? The NLP, autonomous driving, robotics, computer vision, etc. But the problem is that the compute kind of grow exponentially over the years, with a lot of larger and deep neural network. So the compute also grows, significantly. Just to put more clear perspective here, the table just show some of the common neural networks has been used in computer vision and natural language processing domain. So, for example, this VGG16 network, it has a total of 138 millions of parameters. So that's how many parameters you have to optimize in the deep neural network. And that's the 15.5 gig flops you have to use for the compute. So that's a lot of storage and the computing resource required to train such large network. So later we have even more or larger networks developed. Usually these large deep neural network was trained on the powerful supercomputers or GPU clusters. However, in our daily life, right? So in our real world applications, we have a lot of IoT or smart devices like drones, vacuums, robots, surveillance cameras, and the cell phones. So they have some computing capability, but it's not comparable to like GPU server or super computing clusters. So we want to democratize these AI in our daily life, right? So that requires the rethinking of the design or developing the deep learning framework or architecture. So we need this edge-friendly neural network that is able to deploy on these edge device. And also, even if we have the same platform, for example, if we have a drone platform, the computing resource is also dynamic, right? Maybe because of the energy issue, right? You have a low power, then you are not able to run this specific network. So that also requires like dynamic neural network that is able to cope with kind of constantly changing resource. Or we have some of the dynamic communication condition, right? So maybe here you have very good communication bandwidth, then you're able to download large neural networks. But if there's a communication bandwidth becomes smaller, then there's an issue. So we need to think about how to design efficient and adaptive neural networks to for our real world applications. So in the next slide presentation, I'm going to talk about two projects that specifically address this challenge. So the first project is called UbiVision, ubiquitous machine vision with adaptive wireless networking and edge computing, and this is supported by NSF, and it's collaboration with Professor Han in New Jersey Institute of Technology. So the goal of this project is to realize this ubiquitous machine vision and enable efficient utilization of these network cameras for information extraction and sharing. So there's two fundamental research problems we aim to solve. One is how to design adaptive and efficient machine vision algorithm, for resource-constrained smart cameras. The second is how we are able to engineering reliable machine learning frameworks for robust vision analysis on the edge server. So as shown in this figure here, so basically this is like a high-level idea of our proposed framework, right? So assuming you have a lot of smart cameras doing the smart surveillance, and you collecting these video data, right? And you want to extract some of the useful information, and before sending to the edge server for the further processing. So on the edge device, like smart cameras, how can we design this kind of efficient machine vision algorithm, maybe extract informative information, such as we can do object detection, right? We want to extract the car or maybe the people in the scene, right? So later we can send these useful information rather than the entire video frames to the server, because that will occupy a lot of data volume, increase the communication burden. So with these kind of extracted useful information, we reduce the communication overhead. And then on the edge server side, we want to develop a robust or reliable machine learning algorithm to achieve reliable vision analysis, right? Maybe the extracted information somehow is corrupted or maybe noisy, right? Because maybe the object detector on the smart edge device side do not give you like the accurate information about this car, maybe just partial of the car, right? How can you leverage these kind of noisy information to achieve reliable target analysis? For example, recognize what is the model of the car or the make of the car, the color, and also maybe some of the anomalous event in the scene, right? Maybe there's a car accident or maybe some other anomaly in the scene. So that's the overall idea of this project. Through this project, we have several key outcomes. First, we developed a novel deep neural networks training strategy that is able to achieve resource-aware, efficient, adaptive inference at time. So the basic idea is that we're able to develop or train a neural network that is able to slim the network size at different levels, right? So to cope with the resource constraint. So for example, for the resource limited devices, maybe you are not able to deploy the original large neural network, then you can slim it, right, to cope with the computation or resource constraint. You can also think, we also think about from the input perspective, right? Is it necessary to process the original image, right? For some of the easy samples, right, maybe you don't have to operate in the original resolution, just like the human perception, right? If a blur, a low resolution image, you are still able to get the basic semantics of that image. So we do this kind of training to achieve this kind of accuracy and efficiency trade-off, and able to deploy this network in an adaptive way at the runtime. And this approach is able to apply to various tasks like classification, object detection, image segmentation, and video understanding. And is also amenable for distributed learning, for example, federal learning, which I will talk about in the next project. And we are also developing a general regularization method for better training the deep neural networks, because deep neural networks is notorious for require a large amount of data to stabilize the training. So we are able to develop a regularization technique that is able to work with any deep neural network architecture, and it can be applied to various tasks like detection, segmentation, etc. And it's also robust to data corruption. For example, maybe the collected images have been contaminated by noise or maybe some motion blurring, right? So with the regularization technique, the network is able to robust to these kind of data corruption. And also, adversarial attack is a very critical issue in deep learning. So this kind of perturbation is kind of purposely manipulated by some of the attackers. So we also want to achieve adversarial robustness in this sense. And with this regularization technique, the network learned is also can be very effective in the low data regime, right? So you don't require a lot of training data. So if you have a small training data, you're still able to have a very reliable training network. And we also developed several computationally efficient deep learning algorithms for several key vision tasks, like object detection and human pose estimation. So here, just showing a video demo, this human pose estimation algorithm is able to run in real time on this video frame. So this can be applied to several applications like AR, VR applications and gaming. And right now we are also using this kind of human estimation, real-time human estimation algorithm for athlete training program. Okay, so the second project is supported by NSF and Intel. So this is democratized AI through the multi-hop federated learning over the air. So the previous project I talked about is doing the conventional centralized training, right? So you can send the data to the cloud, and the cloud will collect all the data and do the machine learning training. But here, the one risk is that the data there's a data leakage issue, right? So a lot of users, right, the cell phone users, they don't want to share their data to the cloud because of the privacy issue. So here, how can we harness the big data, right, while preserving the data privacy? So that's what we want to address in this project by using the new machine learning paradigm called federated learning. So the idea of the federated learning is that you don't share the data to the central server. Instead, each of the user or local client will deploy a machine learning model and train the machine learning model on the local client, and sending the learned model, for example, the deep neural network, we are sending the model updates or weights to the central server. And the central server will aggregate those model weights to, kind of collaborating all the useful informations to have a strong global model and send back to the local client. Okay, so in this case, the data will never leave from the local client. Only the model parameters will send to the central server. So there's a layer of protection of the data privacy. But to do so, there's also several challenges, right? So because we are involving communicate these model updates to the server, and the server will send back the model weights to the client and do this kind of iterative training process. So communication will pose a significant challenge. And also the second challenge is the system heterogeneity, right? So as I mentioned in the previous project, right, in the real world applications, different users, they have different, platforms, they have different resource. So how we are able to train this kind of collaborative, to perform this kind of collaborative training with this kind of system heterogeneity is also a great challenge. And the third one is the statistical heterogeneity that is related to the data, right? Different data user may have a different type of data, right? So here I may have a lot of image data, but another user may have only audio data or maybe text data. So how we are able to address this kind of data heterogeneity is also a challenge in the federal learning. So the overall solution is that we provide a holistic framework for this fast convergence and robust federal learning. So there's two pillars for this project, and they are interconnected. One is the reinforcement learning-based federated networking, and the second is the network-efficient federal learning, right? How you're able to do this kind of federal learning in the communication-efficient way. And also the third one is the adaptive local model training, right? How we are able to cope with these kind of system heterogeneity in this collaborative training scenario. So my focus was on the third one, the adaptive local training. So specifically, I addressed all three challenges I mentioned in the federal learning. So that's the system heterogeneity. So we leveraged the adaptive network we've developed. So this can be readily applied in the federal learning setting, right? So we are able to, instantly change the network structure and input resolutions according to the resource each client has. So to address this kind of heterogeneity. And for the statistical heterogeneity, we also develop another regularization technique that is able to train the network better, so that is able to generalize well to some unknown data distributions. And to address the communication cost issue, we've also developed the parameter efficient tuning method. Instead of sending all the model weights to the central server, so we are only sending a small portion of the network to the server. This can be adapted to the local data as to their local data distribution. But also this will present a shared part of the knowledge that is aggregated from other users. So for my future research, I'll based on my the research I built up from those two projects, and I will want to basically extend it to this kind of agile intelligence for complex connected system. So there's basically two fundamental research problems I want to solve. One is how can AI network architectures adaptively transform to share knowledge between hosts? And the second is how can large numbers of AI learning systems having disparate training data and then semantic label sets be combined into a scalable AI system, right? So with different AI systems, they have different semantic labels, different training data. How can we, combine these knowledges into like a shareable representation? So to address these, research problems, well, dive into these kind of sub areas of machine learning. For example, the self-supervised learning, lifelong learning, or continuous learning, and also the open set learning and domain adaptation. Also, I want to, based on the success of the two projects, I want to extend some of the research to healthcare, smart manufacturing, and STEM educations. So I'd like to build machine vision algorithm and system, from the perspective of application-driven insight and challenges. For example, in the smart manufacturing and healthcare, right? So the data privacy is a big issue, right? So we cannot share the, those kind of privacy sensitive data, right? So maybe the federal learning can play a key role in this kind of scenario, right? Rather share the data, but we are able to harness the knowledge distributed among different users. And also want to develop personalized computer vision and machine learning solutions for these, applications, right? So again, just using the healthcare and smart manufacturing as application, we are not care about the common knowledge, right? But we also care about develop the personalized solution, especially for this healthcare, right? Can we tailor your solution to a specific individual? So that's something I seeking collaborations, maybe from School of Nursing, School of Medicine, and civil engineering for the manufacturing. Okay, so finally, I want to acknowledge the support from NSF and the industry partner Intel, and also I want to thank the colleagues in CRCV, CS department, and the CECS, and the great support from UCF. And also want to thank my collaborators of this project, and of course my PhD students. They are being very self-motivated and working hard for these projects, and also publish high quality research papers in top venues. Okay.